What does it mean when a comet seems to breathe? 3I Atlas. A traveler from another star system is exhaling 40 kilograms of water every single second into the freezing void, far too distant from the sun for such behavior. Astronomers whisper, with a mix of excitement and unease, that it's acting alive. But this comet story doesn't end with impossible water. There's strange nickel without its partner, iron, cyanide appearing out of sequence, and whispers of an origin billions of years older than our own solar system. Meanwhile, away from this interstellar visitor, citizen scientists stumble upon the largest odd radio circles ever seen. And in our own celestial backyard, Mercury and Ceres align in the October skies with curious timing, making people ask, is there a link to 3I Atlas? And then there's Blue Origin's October flight, a mission that raised more questions than it answered. Did it even happen the way we were told? Stay with me until the very end. We're going to confront these unsettling questions head-on. If these mysteries have you hooked the way they have me, make sure to hit that like button and subscribe so you don't miss a single update as the story unfolds in real time. Drop a comment below. Tell me where you're tuning in from, what time it is there, and whether you believe we're getting the full, unvarnished truth about these world-changing discoveries. Picture this. You're floating in the cold, profound silence of space, more than 3 times farther from the sun than Earth is. Out here, sunlight is a mere whisper. Heat is a memory. Ice stays permanently frozen. Comets in this deep freeze go dormant. Everything sleeps. And then you see it. A comet absolutely hemorrhaging water into the void, pouring 40 kilograms of the stuff into space every single second. This isn't a trickle. It's a flood. Water gushing off a frozen rock where water has no business flowing at all. This is 3I Atlas, an interstellar comet that arrived in our solar system from somewhere else, carrying the rulebook from another star's backyard. And as we're rapidly discovering, those rules don't match ours. The first clue came from an unlikely source. The Swift Observatory, a space telescope famously designed to hunt the universe's most violent explosions, gamma-ray bursts. In early 2025, Swift turned its sensitive ultraviolet eyes toward 3I Atlas and spotted something impossible. A vast, glowing halo of hydroxyl molecules surrounding the comet. Hydroxyl, or OH, is the telltale echo of water screaming as it dies. It's what you get when fierce ultraviolet sunlight slams into water molecules and rips them apart. When you see OH, you know water was just there, and Swift saw a lot of it. The numbers, when they were crunched, were staggering. At a distance of 3.51 astronomical units from the Sun, out in the frigid realm between the orbits of Mars and Jupiter, 3I Atlas was releasing 1.35x10 superscript 2 water molecules every second. That translates to 40 kilograms per second, every second. Let's put that in perspective. That's the mass of a small car being launched into space as pure water vapor every minute, from a distance where every single comet we've ever known in our own solar system is barely a whisper. They are cold, dormant, practically dead. Water ice needs heat to sublimate, to turn directly from solid to gas. And there's simply not enough solar energy this far out to drive that kind of furious activity. Our comets wait patiently until they are much, much closer to the sun's warmth before they wake up and begin their streaming dance of gas and dust. 3I Atlas clearly didn't get that memo. You might remember our first confirmed interstellar visitor, Oumuamua. That thing was dry as a bone. No water, no detectable outgassing, just a silent, tumbling, strangely shaped rock speeding through our neighborhood. Then came 2I/Borisov, the second interstellar comet. Borisov was active, but it behaved exactly like our comets do. It followed the script. It was predictable. It was, in the best possible way for science, boring. 3I Atlas is neither. It's unnervingly, inexplicably alive in a way that shouldn't be possible. It's screaming water into a cosmic silence where silence should reign. And the question hanging over every astronomer who has pointed a telescope at this thing is simple, terrifying, and exhilarating. How? What hidden mechanism could possibly drive this? Is there some exotic ice we don't know about? A substance that sublooms at temperatures we thought were far too cold? Is the comet's interior still warm, retaining some primordial heat from its violent birth billions of years ago? Is it rotating in some bizarre, chaotic way that focuses fleeting sunlight onto hidden reservoirs of volatile materials? Or is there a form of chemistry happening deep within that rocky nucleus that we've simply never encountered before? The water, as it turns out, was just the beginning of the mystery. In the well-ordered world of solar system comets, certain patterns are sacrosanct. They are the cosmic constants we've come to rely on. One of them is this: when comets get hot enough to start sublimating metals off their surfaces, iron and nickel show up together. They are like old friends who always travel in pairs. You see one, you see the other. Their chemical bonds and similar sublimation temperatures keep them locked in a predictable partnership. Except 3I Atlas, it seems, is a rebel that never read the textbook. A team in Chile, using the powerful Very Large Telescope, VLT, and its sophisticated spectrograph, aimed their instruments at 3I Atlas and found something that made seasoned astronomers double-check their data. Nickel emission lines were blazing bright in the spectrum. Strong, unmistakable, impossible to ignore. And iron? It was either completely absent or so vanishingly weak it barely registered. Nickel, without iron. It's like finding smoke without fire. Footprints without feet. In our solar system, this simply doesn't happen. When a comet heats up enough to release metals, iron and nickel appear in lockstep, bound by the same mineral structures and formation processes. This wasn't a glitch. The signal persisted. It was a pattern. It was the comet, in its own silent chemical language, telling us something fundamental and strange about its very composition. The scientific community has floated several explanations, and none of them are simple. Chemical fractionation. Perhaps in the alien environment where 3I Atlas formed, nickel got incorporated into volatile compounds that vaporize easily, while iron was locked away into more stubborn, refractory minerals that need much higher temperatures to sublimate. Picture nickel hitching a ride with escaping ices, while iron stayed behind in rocky grains. Organometallic compounds. On Earth, we have molecules like nickel carbonyl, where nickel atoms bind to carbon monoxide. These compounds are volatile and evaporate at relatively low temperatures. If 3I Atlas formed in an environment rich in carbon monoxide and other organics, maybe nickel got trapped in these kinds of molecules. Sunlight hitting them could cause them to decompose, releasing atomic nickel into the coma, while iron remains locked in solid form. Space weathering. Cosmic rays and ultraviolet radiation can bombard an interstellar object for millions or billions of years. This sustained assault can alter surface chemistry in weird and wonderful ways. Maybe this radiation processing created a nickel-rich rind on the comet's surface, a radiation-damaged layer that doesn't reflect the comet's true bulk composition, an alien origin. The most profound possibility is that 3I Atlas formed in a stellar system with genuinely different elemental abundances. Stars aren't all made the same. Older stars, stars from different parts of the galaxy, stars that formed from gas clouds enriched by different types of supernovae, they all have slightly different recipes. Maybe 3I Atlas comes from a place where nickel was simply more abundant relative to iron than it is in our own cosmic neighborhood. Of course, we must be cautious. Spectroscopy is hard. Detecting faint emission lines against a bright, noisy background is a monumental technical challenge. It's possible iron is there, just below our current detection limits. As the comet gets closer to the sun and heats up, iron might yet make a dramatic appearance, reassuring us that the universe still makes sense. But what if it doesn't? What if 3I Atlas gets all the way to perihelion, its closest point to the Sun, and iron never shows up? What if the nickel-to-iron ratio stays completely inverted compared to everything we've ever seen? That wouldn't just be an anomaly. That would be a revolution. It would tell us that planetary systems can produce comets with metal chemistries so fundamentally different from ours that our models of planetary formation need a complete and utter overhaul. This is why astronomers are watching 3I Atlas with an almost obsessive focus. Every new observation is a test. Every spectrum is a chance to either confirm our understanding of the cosmos or to shatter it into 1,000 beautiful, bewildering pieces. And right now, 3I Atlas is doing a lot more shattering than confirming. Comets are supposed to follow a predictable script. They brighten gradually as they approach the Sun. The physics is straightforward. More sunlight leads to more heating, which leads to more sublimation, which leads to more gas and dust. The relationship should be smooth, predictable, almost boring. Once again, 3I Atlas never got that memo. Observers tracking the comet noticed something strange about its color. Early on, it looked relatively neutral, maybe slightly reddish, typical for a distant, icy body. But as it moved inexorably closer to the Sun, it began to turn. Not a subtle shift, but a vivid, eerie green that became unmistakable in photographs and spectroscopic data. That otherworldly green comes from two primary sources: diatomic carbon, C2, and cyanogen, CN molecules, and, you guessed it, atomic nickel. Both emit light strongly in the green part of the spectrum, and both started ramping up dramatically as the comet warmed. But the increase wasn't linear. It wasn't smooth. It was superlinear, meaning the intensity of these emission lines was climbing faster than simple geometry could explain. When you have your distance to the Sun, you get 4 times the sunlight per square meter. That's the inverse square law, basic foundational physics. But 3I Atlas's emissions were climbing even faster than that. It was as if something was being unlocked. A new process was kicking in. Astronomers call this switch-on behavior. Imagine a specific temperature threshold. Below that threshold, a particular type of ice remains frozen solid, dormant, and locked away. The comet crosses that threshold, and suddenly, that ice begins to sublimate furiously. Gas production jumps. New, previously unseen emission lines blaze into existence in the spectrum. It's like flipping a switch. One moment the process is off. The next, it's on. And once it's on, it can run away with itself if there's enough material to feed it. 3I Atlas appears to have multiple switches. Switch 1, water, flipped on way out at $3.50, which was our first major clue that something was wrong. Switch 2, cyanide and nickel, blazing green as the comet warmed further. Each new emission suggests a different volatile reservoir being tapped, a different chemical environment deep within the nucleus reaching its personal activation energy. How is this possible? Several models attempt to explain it. The icy grain halo. Instead of all activity happening right at the nucleus surface, imagine small ice grains being lifted off the nucleus by escaping gas. These grains float away, still frozen, but as they drift, they are exposed to more and more direct sunlight. Eventually, each grain reaches its own personal threshold and starts sublimating violently. This creates a distributed source of gas, a cloud of icy mist surrounding the comet, which could explain the superlinear brightness increase. Thermal fracturing. Comets are fragile, dirty snowballs. When one part heats up and expands while another stays cold and contracted, immense stresses build up until, crack, a fracture exposes fresh, previously insulated material to sunlight. Suddenly, you have new surface area sublimating new volatiles. The comet experiences an outburst. 3I Atlas might be literally cracking itself open as it heats, revealing layer after layer of its frozen history. The exotic ice onion. water ice sublimates at one temperature, carbon monoxide ice at a much lower one. Carbon dioxide is somewhere in between. If 3I Atlas is layered like an onion, with different ices at different depths, then as it warms, you'd see a sequential activation, a cosmic peeling back of layers, each one a new chapter in the story. We've seen comets in our solar system do weird things, sudden outbursts, even splitting in two. But 3I Atlas is doing this on a schedule and at distances that don't match any of our experience. It's alive where it should be asleep. The switching on in a way that feels almost deliberate. The tension is building. As 3I Atlas continues its inward journey, will more switches flip? Will we see new, completely unexpected molecules? Will the activity plateau, or will it keep accelerating into chaos? This isn't the study of a steady, predictable comet. This is a high-stakes drama, unfolding in real time, against the clock. Every object in space carries a story written in the elegant script of its trajectory. Where it's going tells you where it's been. And the story written in 3I Atlas's path is an epic, spanning billions of years and potentially thousands of light years. Its orbit is hyperbolic, the technical term for an open curve, a path that doesn't loop back. 3I Atlas came from the depths of interstellar space, is swinging around our sun, and will depart again, never to return. Its orbital eccentricity is greater than 1, marking it as definitively unbound, a free agent, a cosmic wanderer just passing through. Astronomers performed precovery, short for prediscovery recovery, scouring old survey data for images of the object before anyone knew it was interesting. They struck gold. 3I Atlas had been photographed multiple times by automated sky surveys, with some images going back to when the comet was a faint 6.4 astronomical units away, still inbound, still cold and anonymous. By stitching these observations together, they reconstructed its path with stunning precision. And that path points outward back into the galaxy, but not to a random address. By combining this orbital data with the star mapping power of the Gaia Space Telescope, which has charted the positions and motions of over 1 billion stars, astronomers can make educated guesses about its origin. The answer is profound. Our galaxy has structure. The stars in the Milky Way aren't randomly scattered. Most, like our sun, reside in the thin disk, a relatively flat, orderly plane of younger, metal-rich stars orbiting the galactic center. But there is also a thick disk, a population of older stars that move on more tilted, eccentric orbits. These thick disk stars are chemically distinct, older, formed earlier in the galaxy's history when there were fewer heavy elements, metals, available. 3I Atlas's trajectory suggests it may be a visitor from this thick disk. Let that sink in. If this is true, if this comet formed in that ancient stellar population, then it could be older than our entire solar system. Our sun is 4.6 billion years old. Thick disk stars can be 7, 8, even 10 billion years old or more. That means the ice and rock that make up 3I Atlas could have formed from a primordial gas cloud before our sun was even a glimmer in a molecular cloud's eye. Chemically, this is staggering. The gas cloud that collapsed to form a thick disk star had a different recipe. Fewer heavy elements forged in the hearts of earlier stars. If 3I Atlas is a relic from that time, its composition would reflect that lower metallicity. There would be less iron, less silicon, less of the rocky elements that build planets. But there would still be volatiles, carbon, nitrogen, oxygen. Maybe that's the key. Maybe its high carbon dioxide ratio, its weird metal abundances, are not bugs but features. Features of a bygone galactic era. This comet isn't just a visitor from another star system. It could be a time traveler, a chemical fossil from the galaxy's wild youth. Of course, tracing an object back through billions of years of galactic motion is fiendishly difficult. Gravitational nudges from passing stars, interactions with spiral arms, they all muddle the trail. But the mere plausibility that we are looking at an artifact older than our world is extraordinary. We might be studying a survivor, a time capsule, and if we could ever pinpoint its original birth cluster, we might someday identify its siblings. Other comets, even planets, ejected from that same ancient system, now scattered like cosmic confetti across the Milky Way. 3I Atlas might be one letter in a message written across thousands of light years. And we are only just beginning to learn how to read the alphabet. Sometimes the most profound discoveries happen not because of a powerful algorithm, but because someone was looking at the data in just the right way, with human eyes, human intuition, and a human brain wired to spot the unusual. Let me tell you about odd radio circles, or ORCs. Discovered only in 2019, these are vast, perfect rings of radio emission, sometimes hundreds of thousands of light years across, floating in the deep field like cosmic smoke rings. Nobody knows what they are. The leading theories involve shock waves from galactic winds or supermassive black holes. But honestly, we're still in the dark. They are genuinely mysterious. Finding them is incredibly hard. They are faint and diffuse, blending into the radio background. Automated detection algorithms trained to find point sources or compact galaxies often miss them entirely. This is where citizen science enters the stage. Radio Galaxy Zoo, LOFR, is a project where volunteers from around the world visually inspect radio maps, looking for things that just don't fit. They're not looking for anything specific. They're looking for weird. In March 2025, a volunteer, staring at their screen somewhere on the planet, flagged something extraordinary. Cataloged under the dry name RDJ, it was a pair of intersecting radio rings, twin circles overlapping in the sky to form a ghostly figure 8. It is the most distant and powerful ORC discovered to date, and it was found not by a supercomputer or a team of PhDs, but by a person donating their time and curiosity. The data came from LOFR, the low-frequency array in Europe, which generates a torrent of information, too much for any professional team to examine by hand. Automated pipelines process most of it, but they have built-in filters. They are designed to catch the expected. The truly bizarre, the things that don't fit any template, often slip through the digital net. This is where human pattern recognition becomes priceless. Our brains are incredible subconscious anomaly detectors. The volunteer who found this ORC didn't need to understand the complex plasma physics behind them. They just needed to look at the image and think, "Huh, that's weird." And they were right. The lesson here extends far beyond radio astronomy. We are entering an era of data deluge. The Vera Rubin Observatory, when it comes online, will generate 15 terabytes of data every night for a decade. No human team can look at all of that. No set of algorithms is perfect. We need both. We need the brute force processing power of machines to handle the bulk, and we need the quirky, pattern-seeking brilliance of the human mind to catch the edge cases, the things that defy all expectation. Now, let's connect this back to 3I Atlas. Could a citizen scientist have flagged its anomalies early? Could someone, looking at publicly available spectral data, have noticed the stark absence of iron next to the nickel spike before the professionals did? It's possible. While spectroscopy is complex, the power of a global community, with diverse backgrounds and fresh eyes, should not be underestimated. There's a long and proud history of amateur astronomers making pivotal discoveries: supernovae, comets, asteroids. They succeed because they look everywhere, unconstrained by the focused, sometimes narrow priorities of professional research. In the future, as the data floodgates open, citizen scientists may well become our first responders to the cosmic unknown, flagging the next interstellar oddity for the professionals to investigate in depth. It's not a competition, it's a partnership. And in the 21st century, it's a partnership we cannot do without. October 2025 presented a beautiful, and for some, a deeply significant celestial tableau. Mercury, the swift inner planet, swung into a favorable evening apparition, shining brightly low in the twilight. At the same time, Ceres, the largest object in the asteroid belt, reached opposition, its brightest and closest point to Earth. On social media, the dots were quickly connected. Mercury is visible. Ceres is visible. And this wildly anomalous interstellar comet, 3I Atlas, is activating. The question was inevitable. Were they related? Was some grand cosmic alignment, some subtle gravitational resonance of the solar system, triggering or amplifying the comet's impossible behavior? Let's be unequivocally clear. No, there is no connection. Mercury's orbit has precisely zero gravitational influence on the outgassing of a comet billions of kilometers away. Ceres's position relative to Earth is cosmically irrelevant to the chemistry happening within 3I Atlas. These are independent events, coincidentally visible from our earthly vantage point at the same time. Nothing more, but we can't help ourselves. We are wired for pattern recognition. It's a deep-seated survival trait. Our ancestors who noticed that certain berries caused sickness, or that specific animal tracks led to prey, were more likely to survive and pass on their genes. So, our brains are hypersensitive to patterns, sometimes to the point of finding them where none exist. This is pareidolia on a cosmic scale. Seeing faces in clouds, hearing messages in static. This pattern detection gone haywire, and it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments and comets. The appearance of a hairy star was a portent of doom, the death of kings, or a sign of divine wrath. A perfect historical analogy is the 1910 return of Halley's Comet. Astronomers had detected cyanogen gas in its tail. Newspapers ran sensational headlines. Comet's poisonous tail will sweep Earth. People bought gas masks, sealed their windows, and there were even reports of suicides by those convinced the world was ending. Of course, nothing happened. A comet's tail is a harder vacuum than we can create in labs on Earth. The panic was fueled by coincidence. The comet's appearance alongside unrelated political unrest, earthquakes, and solar activity. We are seeing the same psychological machinery at work today with 3I Atlas. The comet is genuinely scientifically weird. Mercury and Ceres happen to be visible, and the human brain, craving narrative and order, weaves them together into a story. Facts often lose out to compelling narratives. If the comet's activity is linked to planetary positions, then there is order, predictability, and meaning. If they are unrelated, then we live in a universe where strange, disconnected things just happen, and that can be psychologically uncomfortable. Social media acts as an exponential amplifier for this effect. A theory that would have been dismissed at a local pub can now find a global community of believers online in minutes. Links, images, and charts are shared, creating a self-sustaining alternative narrative that competes directly with the slower, more methodical scientific explanation. The lesson isn't that people are gullible. The lesson is that coincidences are powerful, and our brains are not well calibrated to dismiss them statistically. In a universe with thousands of simultaneous astronomical events, some will align purely by chance. And those chance alignments will feel meaningful even when they are not. This matters because it shapes how the public perceives genuine scientific mysteries like 3I Atlas. It primes people to see conspiracies and grand designs, making the sober, evidence-based work of science that much more difficult. Let's zoom out. 3I Atlas is not an isolated weirdness. Astronomy today is awash in anomalies. Odd radio circles, fast radio bursts, Oumuamua's anomalous acceleration, Tabby's star's bizarre dimming. We are detecting more unexplained phenomena than ever before because our tools are better than ever. This is both exciting and dangerous. It's exciting because anomalies are the engines of scientific revolution. Unexplained observations have led us to pulsars, black holes, and dark energy. They force us to question our assumptions and invent new physics. But it's dangerous because of the hype cycle. Every new anomaly is immediately hyped as a potential alien megastructure or wormhole. The media and the public love it. But when 99 times out of 100 the mundane explanation arrives, a dust cloud, an instrumental artifact, there is a backlash. People feel let down. They start to think science is just wild speculation, or worse, that scientists are covering up the real truth. The key is to hold skepticism and wonder in a delicate, simultaneous balance. You can be thrilled by an anomaly without claiming it rewrites all of physics. You can investigate the most exotic possibilities without becoming wedded to them. You can and must change your mind when new evidence arrives. This is where responsible science communication is critical. When reporting on 3I Atlas, the right approach is to say, "This comet is behaving in highly unusual ways. We are investigating several compelling natural explanations. Here is what we know now, and here is what we're doing to find out more." The wrong approach is, "Alien comet defies laws of physics. Scientists baffled." Nuance doesn't always generate clicks, but it builds long-term trust. We must treat the public as adults who can handle uncertainty, because they can. Most people understand that "we don't know yet" is a perfectly valid, and indeed a very common, answer in science. 3I Atlas is one data point in a growing stack of cosmic mysteries. It is important. It is fascinating. But it is not yet proof of anything beyond a naturally diverse and surprising universe. The process of studying it, of testing hypotheses, ruling out explanations, and inching closer to the truth, is valuable in and of itself. That process is science. And science, done honestly and communicated clearly, remains one of humanity's greatest achievements, especially when it's grappling with things it doesn't yet understand. So here we are, thousands of words deep into the mystery of 3I Atlas, an interstellar comet pouring water into space where water should be frozen solid, glowing with an eerie green light from nickel that has lost its partner, switching on in stages like a machine booting up, carrying chemistry from another star system and possibly from another epoch of the galaxy itself. Is it alive? In the poetic sense, perhaps. It is dynamic, changing, and responding to its environment in complex ways. Its behavior feels purposeful, even though we know it's driven by the blind, beautiful forces of physics and chemistry, not by intention. But is it alive in the biological sense? Almost certainly not. There is no evidence of biology, no metabolism, no replication, no information processing. 3I Atlas is, in all likelihood, a rock covered in exotic ices, heated by sunlight, releasing gas and dust according to physical laws. Yet, those physical laws are producing a spectacle we have never witnessed before. The most compelling explanation remains a natural one. 3I Atlas likely formed under conditions profoundly different from those in our solar system. Perhaps in a colder region where carbon dioxide ice was more abundant than water. Perhaps around a parent star with an unusual chemical signature. Perhaps its surface was transformed by billions of years of cosmic ray bombardment. The organometallic compound hypothesis for the nickel is particularly elegant. It requires specific but not impossible chemistry. Its potential origin in the galactic thick disk is the grandest narrative. If it is 7 billion years old, then we are not just studying a comet, we are analyzing a piece of galactic archaeology. Its ices are ancient, its chemistry primitive, its story written in the first few billion years of the Milky Way's life. Could it be artificial? The evidence provides no support for this. Nothing we have seen requires a technological explanation. Invoking aliens is, at this point, unnecessary. But let's entertain the thought one last time, not as a probability, but as a thought experiment. If you were an advanced civilization and wanted to send something across galactic timescales, You might disguise it as a comet. You'd use ice and rock as a protective shield. You might even engineer chemical signatures to act as markers, designed to be revealed by natural sublimation, piquing the curiosity of any species that developed astronomy. 3I Atlas is almost certainly not that. But the fact that it is strange enough to make us seriously contemplate such possibilities is a testament to its power. It stretches our imagination. It forces us to question our assumptions. It reminds us that the universe had billions of years and trillions of star systems to explore possibilities we haven't dreamed of. That is its true value. The next steps are clear. We watch. We measure everything as it approaches perihelion. We look for iron. We refine our models. And we prepare for the next visitor, because the galaxy is undoubtedly full of them. With new telescopes like the Vera Rubin Observatory coming online, we will soon be discovering interstellar objects not once a decade, but once a month. Each one will be a new puzzle, a new window, and one day, perhaps, we will launch a spacecraft to intercept one, to bring a piece of another star system back to Earth. We will analyze its isotopes, study its minerals, and search its organic inventory for the building blocks of life. We will learn things we cannot yet imagine. Until then, we watch. We measure, we wonder, because that is what we do. We look at the universe and we ask questions. Why is that comet active? Where did it come from? What can it teach us? 3I Atlas is a letter from the cosmic dark, written in the language of water, nickel, and cyanide. We didn't ask for it. We don't fully understand its message yet, but we are listening.